Welcome to AI for Good, the leading action-oriented global and inclusive United Nations platform on AI. Organized by ITU in partnership with 40 UN sister organizations and co-convened with Switzerland. The goal of AI for Good is to identify practical applications of AI to advance the United Nations Sustainable Development Goals and scale those solutions for global impact. In today's session, we're counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end, as we will hold a 30-minute networking session in the neural network. Here you can meet, ask questions to our distinguished speakers, connect, and chat with the AI for Good community. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Thank you very much, Anna, for the nice introduction. A very good day to everyone, and thank you very much for joining. Welcome to the AI for Good Machine Learning 5G Challenge webinar session. My name is Thomas Bascolo from ITU, the International Telecommunications Union. The Machine Learning 5G Challenge aims to create a community to solve network-related problems using AI and machine learning. Today, we are excited to host yet another interesting talk titled From 5G to 6G, the Key Challenges to Overcome. As always, we are counting on you to help create an engaging discussion. If you have a question, just type them in the video feature and we will take them during the Q&A session right after the talk. Without further ado, I would like to introduce today's speaker. We are very excited today to have Slavomir Stanczak, who is a professor of network information theory at Technical University Berlin, and he's also the head of wireless communications and networking department at Fraunhofer HHI. Slavomir was also the chairman of the ITU focus group on machine learning for future networks, including 5G. His guidance during the formative years of the focus group ML5G led to the consensus-based development of the first technical report on ML5G, and it was published as an architecture framework for integrating ML in 5G. Eventually, it led to an ITU recommendation called Y.3172, which is one of the most popular SG13 recommendations in the last few years. And also, it is from this focus group where the idea of the challenge was hatched. So it's quite interesting to have Slavomir with us. In this talk, he will discuss the need to address technical challenges and also introduce 6G research and innovation cluster called 6G RIC, which is undertaking an ambitious and comprehensive interdisciplinary research program to address the challenges associated with beyond 5G and 6G. So welcome, Slavomir, and good afternoon.
Yeah, good afternoon, Thomas.
We are very excited to have you today for this webinar, and the floor is yours.
Okay, thanks, Thomas. Thanks for the invitation and nice introduction. I assume you can hear me well. I will just now share my screen and exactly. So could you confirm that everything is okay?
Yes, please.
Okay. So welcome to my talk from 5G to 6G. The key challenges to overcome. This is just, talk, from the perspective of this 6G research and innovation cluster. here's some basic information about this cluster. So we started last year in August. It is funded with 70 million euros for 4 years by Federal Ministry of Education and Research here in Germany, the German ministry. And yeah, I coordinate this this cluster, and we have, like 20 research institutions, organizations from Germany, and so 32 partners, I think, because you have, for example, several chairs from TU Berlin and so on. So as Thomas mentioned, it's highly interdisciplinary in the sense that we have, people like me, and that who are just, more like in baseband processing, and also we have people just dealing with, for example, hardware design, and I think that this is what is needed to achieve some breakthroughs, on the way towards 6G. So here you can see the strategic goals of this cluster. First of all, the focus is on 6G key technologies, and this is what I am going to talk about today mainly. And also, of course, I mean, in the end, we would like to demonstrate the value of these technologies for selected 6G use cases, but the hub is not so much about, 6G use cases. And we would like to have, create an open test and development infrastructure also, that can be used by startups and small companies. Contribute to a new ecosystem driven by openness. So probably you heard about Open RAN or ORAN, and I think that open radio access networks will play, say, important role in the context of 6G. And yeah, we would like improve conditions for cooperation with industry, and of course, at least in Germany, there is this challenge that we need, young talents. I mean, to attract young talents to this field. Otherwise, I mean, the money is not sufficient. We also need, talented people to work with us and to develop new, the next generation of mobile networks. So here, I mean, this is the view is, this is nothing that, was invented by us. This is just, something like consensus of the community what 6G will be. It's as a mix of digital worlds, physical world, and biological world in real time. So, for example, digital world, you can think about digital twin connected with physical world of things, and biological world, it's mainly about humans, and everything is connected, mixed, in real time. Of course, real time here with respect to concrete, applications. So here, I mean, also a comparison with, say, previous generations. As we started with 1G, of course, and then the transition towards 2G was a revolution, because we went digital and digital voice, and then it was available globally, and so on. And 5G, I think that this was also a revolution, in the sense of business models, because we had we just 4G and 3G was only about telecom industry and classical mobile applications like video streaming and or web browsing. And with 5G we just got or had to talk to new partners from the vertical industry, and they brought new use cases, and this use case also new requirements, and very challenging requirements. Probably you can remember, this triangular with enhanced mobile broadband, ultra reliable low latency communication, and massive access, or for Internet of Things. So now, I mean, the question is, you know, what 6G will be. You know, how can we describe, you know, 6G in 2 words? And then one way is to say, okay, 6G is about intelligence and sensing. Okay, I mean, 5G, you know, intelligence in the sense, you know, artificial intelligence and machine learning is not new. As Thomas mentioned, I also was the chairman of the ITUT focus group on machine learning for future networks, including 5G. But the difference is that, you know, here we are talking about highly integrated, deeply integrated AI. So including, you know, all the layers protocol stack. And the reason is, you know, because we know that communication is expensive and computation is local computation is relatively cheap. So that's why, you know, we need to integrate AI into networks, for example, to enhance the energy efficiency. And then another feature is sensing. And I will talk about this later. So, okay, I mean, there are some new potential applications, and here you have 2 examples, and we will use, you know, probably these 2 use cases to evaluate our technologies. And the first telepresence and mixed realities here, of course, I mean, we have very high requirements in terms of data rates and latencies. And on the other hand, we have mobile robot swarms. And here it's interesting because it is, you know, it can be seen in the context of goal-oriented communication. So you have, for example, robots that cooperate for a common goal. So they don't, you know, compete for wireless resources because they collaborate, you know, they cooperate for a common goal. So that, you know, there is some kind of, this is a fundamental different way of communicating. So that's why, you know, we need also, in order to be efficient and to come up with scalable protocols, we also need to have, you know, some kind of paradigm shift when designing solutions for such applications. So, I mean, this slide I showed in the context of 5G many times, because, you know, the first use case, you know, telepresence and mixed realities, you know, here we need, you know, high data rates. Probably, you know, we have to go towards, I don't know, 100 gigabit per second. Some people are talking about 1 terabit per second, but I think that, you know, this is like a mission impossible. But still, you know, we need to significantly, you know, improve or increase, you know, the achievable data rates. And usually, you know, the system design, you know, like 5G was, okay, now imagine we would like to increase, you know, the data rate by a factor of 1,000, and then this is, you know, 10 mal 10, and then, you know, you can write, you know, the throughput per area, and you know, is equal to the, you know, product of high spectral efficiency, right? And then you have to, for example, increase the spectral efficiency of factor 10. Then you have to, you know, increase density by factor 10, and then, you know, provide more bandwidth also by factor 10. And then, you know, you have a chance or then to increase, you know, the rate of by 1,000, by factor of 1,000. But I would like to point out that if we proceed in this way, then, you know, we will definitely, you know, have some problems with the energy consumption. Because just, you know, if the focus is on spectral efficiency, so in general, this is only at the cost of, you know, decreasing the energy efficiency. Also, you know, if we increase the cell density or network density, so network densification is not a new concept, right? So we have to deploy more hardware. So it means that, you know, it might lead to, you know, higher energy consumption. Also, if we go to higher frequencies to provide more bandwidth, then, you know, the current technology used, you know, for you know, for transmitters and receivers, they consume more energy. So in other words, we you know, we probably, you know, we will have problems with, energy efficiency, energy consumption. And so this is also already a big problem in connection with, in the context or in connection with 5G. But I think that what I'm trying to say here, that we cannot, proceed in this way and to achieve, this or satisfy, all the 6G applications with extremely high data rates, high data rate requirements, and so on. So, and then on top of this, I mentioned that, we are talking about open systems, but also virtualization and cloudification. So you can see, on the right-hand side, that traditional run, run on proprietary hardware and design, and then, the trend is towards softwareization and cloudification. And this is great, provides more flexibility and other things. And but the problem is, especially if you try to implement some run functions in software, right? Then this is not in general is not necessarily energy efficient, right? So this trend, the softwareization and cloudification, is at the cost of energy efficiency. And then here, in particular, the problem is in distributed unit, where, for example, some beamforming functions are implemented, and then this module or this unit, consumes 90 to 95% of the processing requirements of the whole, baseband unit. So here, there is a huge challenge, and this is exactly what we are also addressing this problem. How to virtualize these functions, how to use, hardware accelerators, for example, GPUs, and then there will be a demo next week, in Dresden at this IEEE 5G++ summit. So if you are there, in Dresden, so just you are welcome to join us at the demo, and we can discuss how we try to solve or cope with this challenge. So anyway, I hope that I convinced you that just energy consumption is big challenge, and also important key performance metric. So that's why one thing, if we go from 5G to 6G, definitely we have to extend design dimensions, right? So in 5G and also in previous generations, the focus was mainly on this spectrum usage. Spectrum is expensive, so resource efficiency and the spatial signal processing played a key role in this context. But now, if we we cannot continue in this way, we have to take energy consumption or energy efficiency as a key performance metric when designing new networks. And that's why you have here this new dimension. And this is also quite intuitive. You have to maximize spectral efficiency if the spectrum is scarce. But if you go to higher frequencies and then you have large bandwidth, so it doesn't make sense to use the same solutions, spectral efficient solutions, because there is not so much need for spectral efficiency. The focus moves towards energy efficiency, and that's why we also need fundamental different waveforms, in my opinion. Okay, two additional dimensions, of course, are related to AI and intelligence. I mentioned intelligence and sensing. So first of all, for sensing and intelligence, we need data. So that's why data acquisition, how to capture data, how to acquire data, and so on, and how to in fact also process data. And as I said, we need to process data locally. We need to try come up with distributed solutions that minimize the need for moving bits around, because this is expensive in terms of energy efficiency. So that's why you see you have this third additional dimension, network computing, which is closely related to this deep integration of of AI. So that's in general, this is some kind of paradigm shift in the network design, especially because the spectral efficiency is not the only one design criterion, but also this data acquisition and network computation needs some kind of new thoughts regarding how we design and operate networks. Good. So here you have our technical innovation areas, and in the 6G rig. So you see we have sub-terahertz and so on. I will go through these areas right now and just pose some challenges. And I start with this sub-terahertz. So for me, sub-terahertz is like, below 300 gigahertz. So some people call this terahertz, but terahertz starts, with 300 gigahertz. So we call this sub-terahertz. Millimeter wave for me is, up to 100 gigahertz, 100 gigahertz, 300 gigahertz is sub-terahertz. But also, still we need to just address, I mean, this frequency region, below 100 gigahertz are like between 28 and 100 gigahertz still relevant. There is a lot to do also in this frequency range. So, and the problem is you see the objective that to enable the sub-terahertz frequency for mobile applications. I think that, there's at the moment, you can use these frequencies for point-to-point stationary communication. Nothing is moving. The environment is mainly, to a large extent, stationary. But if things move, then the environment becomes highly dynamic. The channel changes very fast, and this is extremely challenging. So here, I mentioned why sub-terahertz mobile access. So I see if you want to achieve like 100 gigabit per second, so you have to go probably beyond 100 gigahertz frequency. And then the question is how to achieve this 100 gigabit per second. So if you look at the Shannon formula, then you can see that you can play with several parameters, like you can increase power or reduce range, which is equivalent more or less to network densification. But the problem is that the rate only increases logarithmically with the power. So on the other hand, you can increase this multiplexing gain, which is before it's a so-called prelog factor, and then the rate increases linearly with this multiplexing gain, and this is the main focus in below 6 gigahertz. And then, okay, so we can also increase bandwidth, and this is possible if we go to higher frequencies, and this is focus more or less our focus if you think about sub-terahertz communication. But then you have to cope with other challenges, higher noise and path loss, and then this requires more power or high antenna gain, right? So, but then there is a big challenge how to ensure high antenna gain with mobility, and also energy efficiency becomes a big challenge. Scaling of traditional design leads to a disaster, more or less. I mean, here energy efficiency, you see. If you go to higher frequencies, you have P. This is a power you need for transmission, and then also there is a power needed to for hardware to run hardware. And then if you go to higher frequency, things become inefficient. So then the question is how to avoid excessive energy consumption. And I have to say that we don't have at the moment a definite answer to these questions. So definitely, what we have to do is, we have to, and it's not enough, to focus on individual component, right? And it's necessary, to optimize each component to make it more energy efficient, but we need, also synergetic gains, no, enabled by cross-domain analysis. And here there are some thoughts. I don't want to go through this list, but also I would like to point out that, you know, there is this digitalization hype. You know, everything must be, you know, digital domain and even softwareized. And so I think that, you know, this is if we want to, you know, significantly reduce the energy consumption, I think that we also need to start thinking analog, right? So this boundary between digital world and analog world, we have to rethink this, you know. And this is just, there is a first step towards this direction. I mean, towards this goal, a hybrid beamforming. And for me, it's a special case of the so-called analog to information, right? So this is also something, you know, in my potential promising direction. And I hope that we will have some kind of interesting results in this area. So the second, you know, innovation area is related to intelligent radio environments. So here, you know, one important topics are, you know, is related, or topics are related to this reconfigurable intelligent surfaces. So the idea is, you know, I mean, in 5G, you cannot more or less control the environment, right? You have, you know, transmitter, you have receiver, and then, you know, there is the air between them. This is just, you know, the propagation environment. This is the wireless channel, and you cannot control. You have to cope with this, right? So, and now the idea is that, you know, you could use some mechanism to have or influence this propagation channel, to change something, to control, to adapt, to adjust, you know, your channel to your need, or to the need of the application, of the underlying application. So, and here, you know, one idea is to use this, you know, smart surfaces, or here's IRS, intelligent reconfigurable services. They are, you know, passive components, passive in the sense that they don't, you know, radiate some, you know, electromagnetic waves, but they just reflect or absorb. And then you can control this. You can control, you know, how waves are reflected. And this is just something new, because we know, I mean, if we have buildings, objects, they reflect as well, but you cannot control these reflections. Here, you have some electronics behind, and then you can control. You can use this for coverage extension, you know, and then you can also use this to improve, you know, for example, the rank of MIMO channels. The rank is, you know, more or less related to this multiplexing gain. So and so on. And then also you can use it, you know, for you know, to provide some kind of file layer security. Nah? I mean, if, for example, between me and my receiver, there is, you know, eavesdropper, so I cannot send, you know, my signal directly, you know, to the receiver. So I can send, you know, using, you know, such intelligent surface, and then to avoid, you know, to avoid this direct transmission where the, you know, eavesdropper is. There are some challenges, you know, related to channel model. Also, you know, the question is how big these surfaces need to be to have a significant impact on the propagation environment. And also measurements, we just, you know, there is a lot of theory, right, in this area. This is nothing, you know, new, but here, you know, we try to, you know, come up with demonstrators, also provide some measurements, and to, you know, take, you know, practical impairments into account, include, you know, those things. So just, it's not so much on the theory side, but our contribution should be, you know, more on the towards, you know, practical solutions. And now in the end, you know, the question is whether, you know, such surfaces make sense, and if yes, for which frequencies, in which applications, and so on. So there are many questions regarding, you know, related to the use of such surfaces. So then we have a network as a sensor. This is just, this sensing thing. I mean, there is a huge interest, in the industry. Here, the idea is to use, say, communication infrastructure also for sensing services. Sensing is more general than localization, but definitely localization is the, I think, most important say special case of sensing, but also you could have detection or classification. This is just also you can detect objects or you can classify objects, and you can have ranging and things like this. So here you have, here you can see the building of HHI, and then we are implementing something which is called complete street perception. So we use, millimeter wave signals, to detect bicyclists, and also, for example, to warn drivers and things like this. So this is just, one use case, but there are, many potential use cases for this. And here also what I would like to mention that there are, of course, different levels of integration and also different definitions related to these levels. We have, identified 3 coexistence, so that, you have radar systems and communication system, more or less, and then they have to just, coexist in some sense. So it means that they shouldn't mutually interfere each other. Then you have some cooperation. So it's also light integrations, within, for example, 6G, and then there is exchange of data, so for example, I could use communication to enhance sensing, or I could use sensing to enhance communication, and then there is full integration. So, and in the extreme, you use, one pilot signal, one signal for both, for communication and sensing. And then you have some kind of joint design of waveforms. So this is still in discussion. I think that the process will be some kind of incremental. I mean, probably we'll start with some kind of cooperation, and in long term, I mean, the trend will be to full integration, also because of the energy efficiency. I mean, so this might be, the roadmap. Here I mentioned detection of passive objects, right? So you can use, a wireless channel. This is, and then you have the so-called impulse response at the receiver. And then, if there is additional object here, then, you have change in the impulse response, and then you can detect this change, and then you say, okay, something is going on in this, say, here in the environment here, and then if you have some kind of machine learning on top of this, so maybe you can even detect what to localize the object, or to say something, or classify, to say something more about this. So, and okay, I'm not going to talk about this. I mean, this is just slide says that you can do some kind of localization and detection using, massive MIMO systems. In particular, I think that this task is really challenging because, small changes, may lead to, also changes in the impulse response, and this might be, highly dynamic. It's difficult to track this and so on. That's why, I think that, if you apply machine learning to lower layers, to things like this, you have to, maybe, use your domain knowledge, and then, to learn features that, are constant over milliseconds to seconds, right? So for us, for people who work at the file layer, it's really a long time. Seconds is like, infinite. And then also I invariant, for example, to changes in frequency. And then, one such parameter is angular power spectrum, is the average power arriving at the array in a unit of angle. So it means that, if a mobile phone transmits, signals, and it's reflected, at buildings, and you have, array of antennas, then you can you observe something which called this true APS, angular power spectrum. So it's the distribution of the power over the angle, right? And then if you have enough antennas, and if the environment is rich, then you can associate this APS to the position of the user, right? And then if the user moves, the APS changes, and then you can even track the object. Here's estimated APS using machine learning, where you can see some publications of us, and this is indeed as I said, here you have two users, and each user impeach this such a APS function. You have to just estimate them and separate them and associate with the position of the user, so you can do it. And then if you for example combine this APS from several base stations, and even if you combine this with other sources of data, then you can even have really good results, very relatively precise results, localization results. Here, for example, if you have APS, it gives you some information about the direction, and then if you combine this with some kind of range information, then you can, if you combine both information, then you just, you can get better results. Okay, so then, there's this topic 6G connectivity. There is also in 5G, massive connectivity. So this is just, like continuation of this work to massive deployment of devices and so on. But here the goal is, this joint consideration of data generation, information transmission, and processing. This Shannon theory, I mean, you have, due to Shannon, you have this separation of source and channel, source coding and channel coding. And then, it's more or less the transmission is content agnostic. Now, I mean, I think that this was a great idea also for us engineers, because, it gives a solid fundament for research. But as I said, I mean, just if we now approaching, the limits of the capacity limits, and also we have, these fundamental problems with energy efficiency. So we have to think, about the source, or about, how, relevant is information, given the information I have already transmitted, how, fresh is the information, and so on. And this is, what people say, called the semantic communication. Now, semantic here more in the sense of significance. Now, how significant is the information? That's why you can see here the sample. Now, sample is just, the samples, the source, and there is there is not adequate time points, or in a different manner, but it's some kind of intelligent sampler that takes into account, for example, how fresh the information is, and how relevant, and so on. And now, here you have this, is this a paradigm shift? Yeah. If yes, how can we make semantic communications happen? I mean, for some people, 6G is about semantic empowered communication. And this is also what we are addressing in the hub here. This picture is not from me. Is there is this paper I can recommend and to everybody: semantic communication in network system, a data significance perspective. So I mean, the idea is, the figure illustrates what I have already said. Just said. That you take some kind of, you have some additional metrics related to say to the source, to the information, and you incorporate this information into different, at different levels of the protocol stack, right? So, this freshness, it's, is used, by sampling. And here you have, a value. So its value can be quantified as a difference between, the benefit of having this sample and the cost of its transmission and so on. And there is a relevance and priority. So it's just, I think there are some interesting thoughts in this direction, how to, include this significance, of the information at different, stages of this process of, communicating and so on. And I think that this is a promising direction to reduce, the energy consumption or increase the energy efficiency, and also to satisfy requirements of some 6G applications. Also, another important goal is trend is this, a goal-oriented communication. I mentioned this in the context of this robots that collaborate for a common goal. So it's goal-oriented communication. And here in particular, we're interested in this over-the-air computation. So I think that, I gave several talks about this, that we have this broadcast property of the channel, which is channel is under certain conditional computer that can compute sums. And then with, appropriate pre-processing and post-processing, you can, in fact, compute even nonlinear functions. Here you can see, if I have, 3 sensors and then they measure temperature, but I am only interested in the average. So I don't need to, I don't need to transmit individual measurements. I can transmit, I can use the channel to provide to the receiver an estimation of the sum, right? So this is, here, so you don't have, 3 transmissions using TDMA, you have only 1 concurrent transmission. And here the idea is, instead of transmitting individual values, you transmit function values. You can use over-the-air for learning. If you have distributed learning, I mentioned that the trend must go towards distributed computation, distributed learning. So here you have the simple linear classifier, and you see this is a function here, linear function. You can use, if you have different sensors. This was about something related to a vertical federated learning. You can use the channel to harness interference to compute the sum, and you don't need coordination between sensors and establish TDMA channel. You just let them transmit concurrently, use the channel to compute the function for you. And you can with the post-processing and pre-processing, you can compute even nonlinear functions. We simulated this using some data, and the gains are, in theory, at least huge. And then we are trying now in the hub, to come up with demonstrators and evaluate all these ideas. Okay, security is, of course, I mean, I didn't mention that, in addition to this, energy efficiency, of course, security is also key performance metric or driving metric. And first of all, I mentioned that now the trend is, or we are 6G system or 6G network will be open in the sense that we will have disaggregated systems with open interfaces, and there are some concerns about security because open interfaces, for me it's good because just it contributes to the trust. I can just have open systems, so I can check what is going on. But on the other hand, okay, this is maybe provides new opportunities for attacks. Okay. So here, I mean, first of all, we have now a white paper on the archive. It will be presented, in June, and this UCNC conference, where we analyze, the security of Open RAN systems. And there are some interesting conclusions. So you can, if you're interested, you can go to archive and download the paper. Also, what we are, interested in is post-quantum security. It's a it doesn't have anything to do with quantum communication. It may, that you can use quantum computers to solve the problem of prime number factorization in polynomial time. So it means that if we have quantum computers, existing protocols, encryption protocols cannot provide, or are not secure. That's why we need, new solutions, and these are called, post-quantum. This is called, post-quantum security. Here, I mean, this is not new. I mean, there are many. We try to combine this post-quantum security with file layer security for, especially, for IoT applications. And here, key points are, or key enabler for this are secrecy maps. So here it characterizes the confidentiality of the radio environment. So it means that, you have, if you have here, transmitter and receiver, and then you have such a map. So you see, that you can, at each point in this room, you can say, how big is the information leakage? So if there is a eavesdropper close, of course, to the transmitter, then you can expect the information leakage in this position is high. But if you go, if you move away from the transmitter, then the information leakage will decrease. And so that's why, it means that, for example, if the eavesdropper is here, then the amount, the information leakage is low, and then it will be difficult for the eavesdropper to decrypt or to receive any useful information, and so on. And now, of course, I mean, here important or interesting direction is to use this reflecting surfaces to shape this environment. So you can shape the environment to your needs. So, for example, if you have, factory on the shop floor, you have factory in the factory, and then there are places where you just, have guests and things like this. Then, there is some higher risk, for eavesdropping, and that's why you have to shape your environment so that the information leakage to these areas is small, right? So this is just, interesting. I think in very interesting direction. Okay, I will skip this, and then the last innovation area is, about this autonomous convergent networks. And here, first of all, it's about this network automation, monitoring, and virtualized and disaggregated 6G networks. And here we put focus, or I don't want to say that this is the only focus, but we are interested in campus networks, and here in particular in convergence of public and private networks. And there are some challenges and approaches. We identified, for example, extending KPIs to vertical applications and industries, and so on. And then I think that there is a lot of huge potential for innovation in network technologies here in such campus networks, and also especially for AI and network management. And here, we have some running project called KIC, where we just, use, AI, ML methods and algorithms, and to manage and operate campus networks. But also, we optimize across communication and production. So we don't just, split, we have here communication and you have here production. No, I mean, just we use ML. For example, we use production data and communication data to do things better. For example, if you have additional information about, the production, like, rotating machines, and things like this, so you can, for example, better predict fading effects in the channel and so on. Also important topic is here simplification of the campus network operation. I think that this is extremely important topic. And then, of course, we can use here AI and try to use AI to, to simplify this process of operating campus networks, so that also non-expert can do it, or or you don't need this deep expertise, and which is I say some companies, of course, they have this expertise, but if you have like small companies, they don't have it, and then AI can just help here to deal with this complex problem. Okay, big question is, I mentioned that the focus is on 6G technologies, like sub-terahertz and intelligent surfaces. And, the question is, what will be the impact of these technologies on the network management operations? So you also post-quantum security and integrated communication sensing, everything has an impact on the network management operation, right? And here, one example is this, how sub-terahertz networking, and, the big question, is 1 million question, how to ensure, sub-terahertz connectivity and the mobility. And then AI will play a crucial role, no question. And but we have some challenges, right? So large disaggregated networks, and this disaggregated network means disaggregated data, right? So they are not at one point, and distributed over some geographical area. And then maybe I have this different sites, places where the data are just connected via capacity limited links. So we have to avoid large data control transport. And I think that, the most important thing is predict local changes in the network, right? I will just show one slide on this. And also I think that, we will have approach distributed AI placement and at the edge AI fast algorithm with local view. I think that this will be also, traditional machine learning algorithms, closer or deeply integrated, in the network. And then we will have long-term deep AI with global view, and that this will, this algorithm will have access to huge amount of data, will operate on a larger time scales, and so on. So here I just, because I don't have time, so I have to finish. I have to say that this reactive versus proactive mobile networking, today's mobile networks are mostly reactive. So detect the problem, outage, poor performance, anomaly, and respond to the problem by taking appropriate action. So I think that, I'm really convinced that if you want to have, high robustness and or even resilience or something like this, your network must be proactive, anticipate the problem. For this, you need robust prediction and act proactively to avoid the problem. So, and that's why I would like to, this prediction algorithm, right, are extremely important. This will be, this algorithm, prediction algorithm, also AI-based or AI-enhanced, will play a crucial role in the whole story. And there are many applications, and we have another here project, AI for mobile. So only in the context of V2X, I mean networks where just prediction is play a key role, and this will be continue, and then I even think that prediction will be even more important in the context of 6G. So okay, so there are some measurements, but I think that I will stop here. And yeah, thank you for your attention. And just, I hope that we will have a nice and interesting discussion based on this talk. Thank you very much.
Thank you very much, Slavomir, for the interesting talk. Yeah, you covered a lot on what to anticipate for 6G. So without further ado, I would like to invite my colleague Vishnu for the Q&A. Good evening, Vishnu.
Thanks, Thomas. Excellent, as usual. Very, very enlightening talk, Slavomir. Thank you so much. My first question is going to be about data. We struggled with data. So I want to ask you about availability of data. In the last slide, you skipped through the measurement. Yes, measurement campaigns. So could you talk about the kind of data measurement and the availability of data for this kind of modeling, please?
Yeah. So these are, here you can see measurement campaigns we performed, and I don't think that we will be able to provide this data to the community. I mean, to everybody. But we are trying at least, for example, I don't think that we will just, we'll be able to provide measurement data from this measurement campaign, all right? But we also performed some measurement campaigns, for example, in the context of campus networks and so on. And then we are talking to partners because, we are here just, this is a project, and partners, some partners provided the equipment, and of course there are some concerns and so on. And then we have to clarify this. So I hope that maybe, we have here like 5 measurement campaigns. I hope that we just, will be able to provide measurement data, at least from 2, maybe 3 measurement campaigns, so that everybody can use it, for to validate, AI algorithms and so on. But on top of this, I mean, in the hub, we are now planning measurement campaigns, especially for high frequencies, millimeter wave, and then, up to 300 gigahertz. We have, appropriate equipment here at HTI, and the plan is, to make it available. I don't know when, but make it available. I think to everybody as well. Yeah.
Thank you very much. That's we look forward to that data. I want to ask you about standards. So we work together. I know very well, but others may not. You're very familiar with the kind of standards analysis that we do in ITU, pre-standards analysis as well. Where do you see standards impacting this kind of?
So I am okay. So I am not expert in standards. It's for me. This ITUT focus group. It was just like a great adventure, and I learned a lot of new things. I know my colleague here. He's responsible for standardization, Thomas Haustein, and I know from him that. 3GPP started, work on machine learning, on deeply integrated machine learning. I mean, it's not, called 6G or something like this, but this is, definitely, it's the first step towards 6G, because I think that 6G is about this deeply integrated AI, and then I saw, some slides from 3GPP. And, they are talking about, like AI-based air interface and things like this. Definitely, this was not the case, for 5G. This is something, this is a new development.
Thank you so much. There is a question from Michael. I don't know if, but let me ask anyways. This is about metamaterials. Are you or partners working on something like special metamaterials to achieve a degree of adaptability? This is regarding intelligent reflecting surfaces.
No, I mean, we have, I am not materials specialist, I have to say, that, but we have, collaboration. Okay, we have a partners in the hub. This is another Fraunhofer Institute, IZM, and then also IHP, and then there is professor here also at TU Berlin. And so if this is the question, right? And then, we are also talking, to, there is this, I forgot a liquid, I forgot. Sorry for this. So, but the question was regarding this intelligent. Are you or your partners working on something like special? No, the question is no. I mean, we are not. We are not working on materials. You know, we are. This is just we are working on how to use these materials and how to, you know, this electronics to control, you know, the control part. And then, you know, the system view. So first of all, I mean, you take such materials, such surfaces, and then you can perform, you know, measurements and to see, you know, what is the impact of the surfaces on the environment. Then you have, you know, some kind of electronics behind this. And then, you know, we develop this electronics and then try to change something and measure, you know, how this impacts, you know, the environment. Because we are talking about this intelligent, you know, radio environments where you can control shape, you know, the environments. But, you know, the crucial question is, you know, what is the impact? Nah? I mean, can I significantly change, you know, the radio propagation environment? Yes or not? And then this, of course, depends how big the surface is. And this, in turn, depends on the frequency, right? The lower frequency, the bigger surface. And if you go to high frequencies, you know, the hope is that, you know, you will get something that is reasonable, that is not so. I hope that this is, you know, an answer to the question.
Yeah, thank you so much. Let me try to ask one more last question about the inference latency and the time budget that we have for inference. You did talk about the Angular scheme that you talked about, APS. Then in that slide you did talk about milliseconds budget. Now the question is that how much of inference time budget do we have for such use cases, and what is the time criticality for inference? Can we are there such studies that you're doing for time budget for inference?
Yeah, this is exactly, I mean, the demo I showed here. So here we have, you know, we are below 1 millisecond. And so, I mean, this is still, I mean, learning, data driven, because it's not model based, right? So it's, we don't model, you know, I mean, we engineers, we have models like, you know, for example, if you have multi-user systems, and so we try to model, and then we develop algorithms based on the model, right? Here, we don't model. We just, you know, take data and then try to extract some information out of the data, and then parameterize, you know, the receiver, you know, to do detection and even interference separation and interference reduction and things like this. But here, you know, we have, you know, for training below 1 millisecond, and now it is completely softwareized. And but we use GPUs as hardware accelerators, right? And then I mentioned once, I think that, you know, in one of our focus group meetings, that, you know, we use GPUs for massive parallelization. So in an algorithm, they are just, you know, usually, you know, if you have, you know, iterative algorithm, then, you know, you have a sequence of operation, right? And then of operation that depend on each other, and this takes time. So now you have to, you know, design an algorithm that can be, you know, parallelized. So you need, you know, huge amount of tasks that can be performed in parallel, and then, you know, and then in the end, you know, you just combine the results and then, you know, get what you want. But if you are able to do this, you know, this massive parallelization, then of course you can dramatically, you know, reduce, you know, the latency. And now, you know, for example, if we for this task, there is even, you know, here YouTube video you can check if you are interested. So if you use MATLAB, this task, the time needed to perform the task is 40 seconds. And then if you have naive implementation on GPU, I think that it's like 6 milliseconds. And then, through massive parallelization and then this coarse design of software and hardware, we could, I think, go below 1 millisecond, 0.6 milliseconds. And this is what is, necessary for some, real-time applications.
Very interesting. Thank you so much for sharing that insight. I know we are running out of time, but let me ask, Srinivas is asking a really interesting question. He's asking, you gave an example of hybrid beamforming. Are there other such examples where analog plus digital gives us benefit? We, in the sense ITU did a challenge where channel estimation was another example. And last year we did, I think modulation prediction was another example. But are there more examples like this where analog and digital gives us more benefit?
Yeah, okay. This is, of course, I mean, there is a lot of, work in this direction, this 1-bit quantization and so on. So in fact, I mean, this, because, the problem is, ID converters, né? So, sampling rate and quantization precision and so on. And I think that there is a lot of work, how to reconstruct a signal or, extract the necessary information using, some kind of cheap AD converters, using, you can play with sampling rate and then, this quantization precision. And so there is a lot of work on this. What we are interested in, and this is a little bit, it looks like, a mission impossible. So, we would like to, for example, you have, if you have the superposition of signals. So you can, for example, in analog domain, you can add signals. This is quite easy, right? But in fact, due to, there is a so-called Kolmogorov superposition theorem. You can, use this, as a basis, to compute functions, even, in theory, you can compute any function. Of course, in practice, it's not true. But in fact, I mean, if you take this theory as a basis and say, okay, in analog domain, I could perform functions that are usually performed in the digital domain, right? So now what we are doing right now is to understand, how to split, this is some kind of functional split between analog and digital, right? So, this hybrid beamforming, I think that this is a very good idea. And because the question was, are you mentioning hybrid beam is a good example? So I think, okay, this is not the question. Okay, this is a good example, right, of this. Except for this, I know some kind of task. It is, I mean, for example, Jonina Elder, I think that she has some papers, about this task-oriented hardware design and so on. So there are some, works in this direction. And then, except for this, I know this, 1-bit quantization and so on. But we just, are now thinking how to split the functions. So coming a functional split between analog and digital. And then, of course, if once we have the split, we want to think, whether it's possible to implement some functions, in analog domain. But I don't think that we will, in the end, have a chip or something, It's more like, to provide foundations maybe for future works. Nah?
Okay. Thank you so much. That's gives me a lot of pointers. One last one from Marco. Marco is asking, semantic communications will take over everything, or is it applied for specific purposes, specific use cases?
I think so. I am not, a big expert in this area. I mean, we work on this age of information and so on. But I think that, this strict separation between communication and application doesn't make sense. It's a waste of resources. We communicate to match too much information. I say communication is expensive, right? It costs a lot of energy. So if I have a controller I control temperature or something else, and the controller uses the average of individual measurements. It doesn't make sense to transmit individual measurements, right? We have to develop protocols that are able to convey, to transmit, the information which is necessary and sufficient to compute the average or to estimate the average. This is, and also there are many sensor networks, and in many areas, I cannot, say much about this, but you can imagine that you have distributed networks, you could have swarm of drones or things like this. And then they have to collaborate together, for some common goal. For this, you need communication, right? And there is no, central point to do it. You have to do it in a distributed manner. So now, please, use TDMA for this coordination. It's extremely, and the protocol or such protocols do not scale with the network size, right? So it's extremely difficult to implement, in a distributed manner, because you need a lot of coordination between, how to access the channel, how to avoid interference and so on. And then, it doesn't scale properly with the network size. So definitely, I think that we need here goal-oriented communication, and also we need, to take, semantic into account. It's not new. I mean, I am also control guy. They have, like event-triggered control, right? And then depending on how big is demand for control, they adapt to this. And then we have to do this on the communication side.
Thank you so much, Ramir. That's a detailed answer. Every time we are way beyond what we talked, but thank you so much for staying back and answering all the questions patiently. A lot of insights. I am sure the audience really appreciate it. Back to you, Thomas.
Thank you so much, Vishnu, for taking care of the Q&A. I would like to thank Slavomir for taking time in your busy schedule to be with us today and share these interesting insights from 5G to 6G and the challenges that are expected. So thank you once again.
Thanks a lot for the invitation, and have a nice and peaceful day.
Thanks. I would like to make one announcement. We have a webinar next week, which will kick off the problem statement for the 2022 ITU AI and Machine Learning 5G Challenge. So make sure that you join the session next week to introduce the first problem statement. We will announce later about details on the registration, but we have first problem statement introduction. At this point in time, I would like to thank everyone for joining today's session, and we haven't finished yet. Let's meet in the neural networking, network for chat, and we can network there. So thanks a lot and see you.
Thank you for participating in today's AI for Good session. We hope you've learned something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the satisfaction survey, connect with interesting profiles, or speak one-on-one using the chat and video function. After the 30-minute networking session, we invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits and poster boards, and build your personalized AI for Good program. It was a pleasure learning with you today. See you at the next AI for Good.